Okay, so welcome to the afternoon session. And we start with Mase-san, who is going to explain how to compute the degree growth in a lattice equation based on singularities. 50 minutes, Mase-san.
Thank you for the introduction. Today I'd like to talk about how to rigorously calculate the degrees for lattice equations from singularity pattern. Okay, so my talk is based on this preprint. So this is the outline of my talk. First, I'd like to talk about the basic things like degree growth, singularity confinement, Halbert's method, and so on. Then, these four parts are the main part of this talk. First, I'll explain how to calculate degrees for lattice equations without rigorous discussion. That means this is the practical part of this talk. And the second part is the theoretical part of this talk. So this part, thanks to this part, the calculation done in this section is justified. And maybe I don't have much time to explain how to calculate singularity patterns, but there are a lot of propositions in handy. And then I'll talk about examples. Okay, so let's get started. Okay, so first I'll explain the degree growth of the mapping on this example. This is a degenerated QRT mapping. So let's take x0 and x1 as initial values. Then every iterate can be written as a rational function in these variables. For example, x2 is this. So the degree of the numerator is 2 and the denominator is 1. So the degree of x2 is 2. And the degree of x3 is 4 because of this. This is degree 4 part. And degree of x4 is 6 because this is degree 6 part. But a cancellation happens here. When you calculate x4 from x2 and x3, this factor should appear in the denominator here. But because of cancellation, it disappears. And that lowers the degree. And a cancellation happens even after that, so at each step. So the degree of x5 is 8, and the degree of x6 is 10, and so on. So thanks to the Laurent property, I mean, the denominator is always monomial. Thanks to the Laurent property, you can easily calculate the degree like this. So the degree growth of this equation is linear. Okay, so we are interested in the degree growth. That means how fast the degree grows. So this value and this value are important. This is called the algebraic entropy of an equation, and this is called the dynamical degree of an equation. And it has a lot of good properties, but what is important is this. Okay. The discrete integrability in this talk is defined by zero algebraic entropy criteria. So if the entropy is 0, then the mapping is called integrable in this talk. But the problem is, these values are always well defined in the autonomous case, but the problem is calculating these values is not easy at all for a concrete equation. That's the biggest problem about degree growth. So in the case of mapping of rank 2, a lot of results are known like this, but this is the biggest result done mainly by Dillard-Favre. If phi is a mapping of rank 2, then the degree growth has...
excuse me, I have a question about integrability. So is this a definition or is it a statement?
It's the definition in this talk.
Okay.
I don't go any further.
Okay, okay, thank you.
Yeah, it's a complex topic, of course, yeah. So, yeah.
Sorry, may I ask another question?
Yes.
Could you just remind what is the definition of a birational mapping of rank 2?
Sorry,
Could you remind what is the definition of a birational mapping of rank 2?
Birational mapping? Oh, birational mapping is a rational mapping with rational inverse. So, for example, this can be written as a birational map on P2. And the inverse is also rational. That's why this is birational. So if you can solve the equation in the opposite direction with rational function, it's birational. Yeah. Okay, so if a birational mapping of rank 2, phi is a birational mapping of rank 2, then there are only 4 possibilities about degree growth: bounded, or linear, or quadratic, or exponential. The first 3 cases are integrable cases. And this is non-integrable. And there are a lot of things are known. Like if the degree is bounded, then phi is almost trivial. If the degree is linear, the degree of growth is linear, then the equation is linearizable via rational transformation. And if the degree growth is quadratic, then the equation is related to an elliptic function, because the equation preserves a elliptic fibration. That's why it should have something to do with elliptic function. And if the degree growth is exponential, then no invariant fibration. That means no invariance. And there is no non-trivial commuting mapping. This is shown by Kanta, yeah. But if the rank is 3 or more, no general classification theory is known yet. But today's main topic is not mappings. Today's main topic is lattice equation. So let's think about the degree growth of a lattice equation on this example. This is called a discrete Liouville equation. And let's think about this initial value problem, meaning red variables are initial values, and then every iterate can be written as a rational function in the initial values. And this is the degrees. And the degree of x and m is n plus m. So it grows linearly. And this equation is known to be linearizable. Let's look at another example. This is Hirata's discrete KDV. Yes, but it has a parameter lambda. If lambda equals 1, it's integrable. And if lambda is not 1, it's not integrable anymore. And the degrees in the case of lambda equals 1 is this. It grows not very fast. But if lambda equals 2, it grows really fast. And if lambda equals 1, the degree grows polynomially. And if lambda is not 1, degree grows exponentially. So a lot of equations are analyzed in the context of degree growth, but there is no general theory yet. But this is a common belief on the degree growth of lattice equations. If the degree growth is linear, then the equation is linear. If the degree growth is polynomial, then the equation is integrable. I don't define discrete integrability here. Okay? Yeah. This is just a common belief. This is not a mathematical statement. Okay? So if the degree growth is exponential, then the equation is not integrable. Yeah. This is a common belief. But again, there are 2 big problems. How to calculate the degree growth for a concrete equation? And no general method has been established yet. And there is one more problem. No general classification theory or anything is known yet. So today, I'd like to explain a new method to calculate the degree growth with all the degrees for a concrete equation from singularity pattern. Okay, but before that, before going to the main part, there is another important remark. In the case of lattice equations, the degree growth strongly depends on the choice of initial value problem. So before, I took this domain, like first quadrant, and this is also first quadrant. First quadrant is okay, but if you take some pathological domain, even an integrable equation like Hirata's KDV can have exponential degree growth. If you're interested in this phenomena, I recommend this paper. So what we should do is to avoid a pathological domain. I don't explain what is a pathological domain in this talk. And we should consider individual degrees instead of total degrees. All the degrees we've seen until now were total degrees. For example, okay, don't forget, but the total degrees. But total degree, what is the total degree? The total degree is the degree with respect to all the initial variables, meaning each initial variable has degree 1. This is the normal degree. But individual degree is a bit different. An individual degree is the degree with respect to an arbitrarily fixed one of the initial variables. So the fixed variable has degree 1 and the others has degree 0. That is the definition of individual degree. So there are a lot of choices of initial variables, of course. So in this talk, we'll be focusing on individual degrees, not total degrees. So let's change the subject, singularity confinement. So yesterday we had 2 talks about singularity confinement, but let's review it briefly. Okay, let's take this equation as an example. K is even integer, even positive integer. And suppose xn minus 1 is some generic value, and xn spontaneously becomes 0. So alpha is generic, so this condition has 1 degree of freedom. But the next step is this, infinity to k, to be exact. But this has no degree of freedom anymore. So the information on the initial value alpha is lost. So this is the definition of singularity. And what happens after that? Let's introduce an infinitesimal parameter epsilon and start from this initial value. Then xn plus 1 is epsilon to minus k, and xn plus 2 is minus epsilon. And a miracle happens. A miraculous cancellation happens here, and xn plus 3 is alpha plus something. But the information, the lost information on alpha is recovered. That's why this singularity is said to be confined. So this pair has 1 degree of freedom. That's why this singularity is confined. And the singularity pattern consists of the values and the multiplicities. So 0 from here, epsilon to 0, and infinity to k from here, and 0 from here. And this is not a singularity anymore. So the singularity pattern of the singularity is this. And this is not a singularity, but the equation has another cyclic pattern. So if you have this pattern, you have to start with a special initial condition, like x0 infinity or x1 equal infinity. But this continues forever, and also in the opposite direction. But this continues forever. But this is not a singularity in the strict sense, because the degree of freedom of every pair is 1. So this is not a singularity, but this pattern is really important in the next page. So let's review the Halber's method without
Sorry,
discussion.
which equation has this singularity pattern? The cyclic pattern? When you say the equation has a cyclic pattern, which one is it?
This equation has this pattern. If you start from x0 equal infinity, then x2 is infinity, and x4 is infinity, and so on. That's why the equation has this pattern.
Okay.
Yeah. Okay, so let's review the Halber's method on the same example. Okay. We'll focus on the degree with respect to x1, so say z. And x0 is just a generic numerical value. And think of xn as a one variable function in z, okay? U is just generic, and Z is variable. So xn is a function in Z with coefficient C. Right? We work over C. And dn0, let dn0 be the number of primitives of xn of 0. And dn infinity is the number of primitives of infinity. And in this talk, we count the number of primitives a lot of times, but every time we count with multiplicity. I won't mention this anymore, but every time the number is counted with multiplicity. So, and by the way, P1C is C and the point infinity. Okay. The essential formula is this. The degree of a rational function, degree of one variable rational function always coincides with the number of primitives of any value, especially 0 and infinity. Okay. Using this, we can calculate the degrees. So this is this, and this is this. So these two values are the same. So what we have to do is to know when xn becomes 0 or infinity. We have to know all the possibility. Okay. Okay, so let's think about xn z spontaneously becoming 0. What happens after that? Because of the singularity pattern, this xn plus 1 is infinity to k, and xn plus 2 is 0. And other things, other iterates are non-zero, non-infinity. How to show that? Good question. How to guarantee no other possibility? I won't explain this because this is without rigorous discussion. Okay. Yeah. But this is a fact. And so x and z star can become 0 if at least one of one of these happen. If xn spontaneously becomes 0, then xn is 0. This is just tautology. And if xn minus 2 spontaneously becomes 0, then because of this pattern, if this xn minus 2 is 0, then this is xn, and xn becomes 0. And no other possibility. How to show that? Good question, but I won't answer that question. In the mapping case. Okay, and how about the infinity, the value infinity? Xn, so there are only two possibilities. If xn minus 1 spontaneously becomes 0, then because of this pattern, if this is xn minus 1, then this is xn, and xn is infinity to k. So the multiplicity of infinity is k. And there is a cyclic pattern, this one. This pattern is important because it generates infinity, the value infinity. So if z equals infinity and n is odd, then xn is infinity. And no other possibility. Why? Don't ask me. Yeah? But this is a fact. So the biggest question in this page is how to guarantee no other possibility. But yeah, I won't answer that question. And let's move on to the calculation part. Okay, let Zn be the number of spontaneous occurrences of xn equals 0. What is the definition? Good question. But I don't answer that question in this page. Okay, so let's assume this is well defined. Then, and we assume there's no other possibility things. Okay? Then we have this relation. I call this degree relation. Each expression is called degree relations by me. Okay, so the degree coincides with the number of pre-images of 0. And this is Zn plus Zn plus 2 because of this pattern. Other than these patterns, there is no possibility of xn becoming 0. And the number of the number of pre-images of infinity is this and this. This corresponds to the pattern this, and this corresponds to the cyclic pattern. So this sum equals to this sum. So we have this relation, and this is a recurrence relation for Zn. So we can solve it with these initial conditions. So we can calculate Zn, and the degree is calculated from this. So we have degree, the degree growth. And of course, you can have the detailed degree expression, but I don't need it here. So the degree growth is like this and this, exponential degree growth and polynomial growth. Okay, so what is the definition of a spontaneous occurrence? That's a big problem. Okay, so Halbar's method has a lot of problems to be solved. Okay, number one, how to guarantee another possibility? Oh, this is very important but difficult. And what is the rigorous definition of a spontaneous occurrence of xn equals 0? And when xn spontaneously becomes 0, is this really true? I didn't prove anything mathematically, right? So we have to prove this. How? Good question. Okay. And question 4. We had degree relations. So we were able to solve it. But is it always the case? The answer is no. Sometimes the number of linear equations is not sufficient. But what is the condition? And there is another minor problem. How can we rigorously show that the pattern is not cyclic? Cyclic means, so we said x and z star is not 0 infinity other than these. How can we prove that? This is not a problem of Halbar's method, but it's a problem of singularity confinement. I don't know how to elementarily show this, but this problem should be solved in the future. So the Halbar method has a lot of problems so far. But I don't answer these questions in the mappings case. Instead, I generalize the method to lattice equations and answer these questions in the lattice case. Because for me, lattice case is much easier than the case of mappings. So let's move on to the main part of this talk. So let's consider the lattice version of Halbar's method on this example. This is the first ever example of non-integrable equation with confined singularities, and it is I who found this. But anyway, so this has a confined singularity pattern. K must be even. If K is not even, then this singularity is not confined anymore. This singularity pattern. But what is the meaning of the singularity pattern? Now, thanks to yesterday's talk, you now understand the meaning of this question. But in this talk, the meaning of this is this. So red variables are initial values, and red dots are just variables, and this is 0. So we introduce epsilon here and start calculating, and they have 4 special values, and these are regular values, meaning these depend on some other initial values. And we don't have to calculate any further. So these are unknown. We don't need it. That's the meaning of this pattern in this talk, only in this talk. Because only this information is necessary in this talk. That's why. In this talk, I'm not explaining the true meaning of singularity confined to anything. I'm just interested in calculating degrees. Okay. So let's fix a domain. And let's fix an arbitrary one of the initial variables, say z here. And calculate the degree xtn with respect to z. And dtn is the number of primitives of 0, and dt infinity is the number of primitives of infinity. And calculate the degree using this relation. We are still working on C, so we have these relations. Okay, so the question is, when does xtn become 0 or infinity? Okay, if xtn spontaneously becomes 0, a movable pattern appears. So this pattern, confining pattern. Okay. And if z is 0 or infinity, then fixed pattern, something special appears like this. And this goes forever, this goes forever. And no other possibility. How to guarantee this? That's one of the biggest questions in this talk. And I'll answer that later. But this is a fact. Okay. So in this section, without rigorous discussion. So wait for the next session if you're interested in the theoretical part. Okay, so only this possibility, only these possibilities. And ztn is the number of spontaneous occurrences of xtn is equal to 0. Again, what is the definition? I'll answer that later. The degree relation. Now we have degree relations. This is the number of primitives of 0, and this is the number of primitives of infinity. The delta, Kronecker delta, corresponds to fixed pattern. For example, we have 0 here, x1, 0. Right? That's why we have Kronecker delta here. So this sum equals to this sum. So we have this evolution equation for z, tn, and the initial conditions are like this. So we can solve this. This is just a linear equation, so we can solve it. We should be solving it. And the result is this. If k equals 2, then yeah, we are interested in degrees. The degree grows really fast. Yeah, the degree growth is in fact exponential because of this relation. Right? This k is 2 or more. That's why the degree growth is exponential. Okay, so the problems related to the lattice version of Halvard method, the first 4 are the same as the mapping version. The question 5 is, what is the definition of a singularity? Yeah, we have to think about this. And question 6, how to deny the possibility of a strange pattern? What is a strange pattern? Because we didn't calculate the outside region. So something might happen. Yeah? So we have to deny such possibility. That's question 6. So let's move on to the theoretical part. Okay, so for simplicity, we focus only on quart equations. So I stop explaining on examples. Now we're in the theoretical part, so everything should be explained theoretically. So we're interested in this equation. This is just a rational function in 3 variables, not necessarily birational. And let's fix a domain, not pathological domain. Then the initial boundary is defined like this. And fix an arbitrary one of the initial variables, say z, and we consider the degree of xtn with respect to z. So the basic strategy of my method is to clarify on which initial variables z star depends. Z star is the value substituted for z. So we must quit substituting generic values for the initial variables other than z. So we should think of each initial variable just as a variable. So that initial variable is just initial variable, not a value, not a scalar value. Okay. So we introduce K. K is the rational function field in the initial variables other than Z. Then xtn. In this setting, xtnz belongs to this field, the field of rational function in Z with coefficient K. But we have to work on an algebraically closed field, so we have to work on K bar, the algebraic closure of K. Then, and we substitute some value, meaning Z star belongs to P1 K bar. This is a very big field. But if we substitute Z star for Z, then xtnz belongs to P1 K bar. Because K bar is algebraically closed, we have this relation for any alpha. The degree of a one variable rational function coincides with the number of preimages of any value. And an important case is that xtn Z star belongs to P1 C. That means this value doesn't depend on other initial variables. So this leads to the concept of constant singularity. The next page. So let's define what is a singularity in this talk. The constant singularity in this talk happens if xtn Z star belongs to P1 C. Z star might depend on some other initial variables, but if xtn Z star belongs to P1 C, then we call it a singularity. And we can define the multiplicity of this singularity as a multiplicity of a rational function with some value. If this is not a constant singularity, then we should think the multiplicity as 0. And this is the definition of singularity pattern. Okay, so let's think about some value Z star. Then the singularity pattern corresponding to Z star consists of these data. This is the singular locus, the points where xtn is a singularity. And its values, their values and their multiplicities. These data are a singularity pattern. And we define some properties and singularities. A constant singularity pattern is fixed if Z star doesn't depend on any other initial variable, like Z star equals 0 or Z star infinity or something like that. And the singularity is movable if it's not fixed. That means the singularity is movable if Z star belongs to this. So Z star does depend on some other initial variable. And singularity pattern is confining if it only has finitely many constant singularities. And a singularity pattern is solitary if it has only one singularity. This is a bit strange. And this is kind of different from the classical singularity confinement theory. Okay, let's look at examples. Okay, this is the same equation as before. And this equation has a movable pattern like this. So 4 constant singularities. And this is movable because Z star is not a scalar. And this is confining because there are only 4 singularities. And this is not solitary because there are 4 singularities. I don't have much time. And this is a fixed pattern corresponding to Z star equals 0. And it goes forever. So this is fixed because Z star is 0. And this is non-confining because this goes forever. And this is not solitary, of course, because being solitary means being confining. And this is also the same, corresponding to Z equals infinity. This goes forever. And this is a bit strange. This star is called alpha, and alpha is a scalar value other than 0 infinity. Then no other constant singularity. So in the classical theory, in the context of singularity confinement, this is not considered as a singularity or pattern or anything, because this is meaningless. But in my talk, we have to think about this kind of pattern. So this is fixed, and this is confining, and this is solitary. And this is a movable solitary pattern. Alpha is a scalar value with other than 0 infinity. Okay, so let's define the basic pattern. This corresponds to the singularity confinement calculation in this talk. So x star is some scalar, and we start from these initial values. The red points are just variables, and this is scalar, and we calculate the pattern. This is called the basic pattern. And of course, this corresponds to the singularity confinement calculation we've seen before. So what we are expecting is the pattern, the basic pattern, corresponds to a movable pattern like this. But we need some conditions for that statement. So for technical reason, we need to impose two conditions: d-factor condition and the basic pattern condition. This is the d-factor condition, but this is just technical thing, and I don't have much time, so I just skip it. Most equations in the literature satisfy this. This is just technical thing. And this is basic pattern condition, and this is also technical. And I'll explain the meaning of this condition later. So I just skip this condition. And let's move on to our main theorems, from theorem A to D. This is the first theorem. The equation satisfies some condition, and this is domain, and this star is some value. Then, and think about the singularity pattern. Then this set, this is the singular locus. The singular part has a unique minimal element, so minimum element with respect to the order. So there is no strange pattern like in next page. And the basic pattern condition is not necessary. So the singular part has a unique minimal element. So we call it the first singularity, and its value, the starting value of the pattern. So this pattern does not exist because this block starts from here and this block starts from here, but these 2 points are both minimal. So because of the theorem, this pattern doesn't exist. No pattern like this. This is the same. So no pattern like this because these 2 points are both minimal. So this is the next theorem. Okay, so some conditions like a d-factor condition and domain, and let's consider the first singularity of a pattern and the basic pattern condition. Then this region, okay, this is the first singularity of a pattern, of this pattern, and this region coincides with the basic pattern. The basic pattern is this, right? So this part corresponds to the basic pattern, meaning, so this is the first singularity. So this part can be thought of as if initial values. That's the meaning of this theorem. And I don't have much time, but yeah. But this is a scalar. So we have to prove that these points marked with plus are algebraically independent over C. And this point and this point are algebraically independent because of the basic pattern condition. That's the meaning of the basic pattern condition. This is the first singularity, and this point are algebraically independent. That's the basic pattern condition. And this point is influenced by this initial value. This point influenced by this initial value. So that's why they are algebraically independent. These 2 points are special. So that's the sketch of the proof. So now, Now we know every movable pattern is governed by the corresponding basic pattern. Okay, and this is the next theorem. That don't try to read this, okay? Don't try to read this. But this is the degree relation. This is the degree relation. So the meaning of this theorem is the number of spontaneous occurrences of X is something is rigorously defined, mathematically defined. I don't explain the definition, but it's defined. And the degree relations are rigorous and exact. So the counting of the number of images is precise. That's the meaning of this theorem. And then, of course, there are some assumptions like the Hepton condition, the basic pattern condition, and the third assumption is important. We know all the singularity patterns that contains a singular value. What is a singular value? The singular value is the value we look at the value as the number of pre-images. Okay. And theorem D. When are degree relations solvable? If the number of starting value is equal or greater than the number of singular values, then it's impossible to solve the degrees. So the degree relations are underdetermining, so there are a lot of solutions. If the starting values are all contained by singular values, then we can solve the relations. So what is important is that the existence of a P1 value that is not a starting value of any movable pattern. And the sketch of the proof is really important, really easy. Count the number of equations and the number of variables, then you have the result. So a P1 value that is not a starting value of any movable pattern is important. So let's look at this on this example. So the list of movable patterns is this: confining pattern and solitary pattern. Of course, confining, but confining pattern, this pattern starts from 0. But then this solitary pattern, it starts from alpha. Alpha is not 0 infinity. So there is no pattern starting from infinity. That's why we can solve the degree relation and we can get degrees. This is the meaning of theorem D. Okay, so but I only have 7 minutes, so I just skip this. So there are a lot of propositions to detect singularity patterns. Oh, by the way, this pattern does not exist. This is a cyclic pattern-like pattern, but cyclic pattern-like thing doesn't exist in the case of lattice equations. And this is about solitary pattern, solitary value or something, and this is about the existence of the special value. I mean, this P1 value that doesn't appear as the first singularity of movable pattern. But let's look at examples. Okay, so let's calculate the degree of the modified discrete modified equation. So this equation is written like this, and let's take this initial value problem, and let's calculate the degree with respect to z. So this is the list of all the singularity patterns of this equation. Solitary one, but gamma is not plus minus k or plus minus 1 over k. This is movable or fixed, depending on the location. And this is a confining pattern, movable, starting from plus minus k. And this is fixed, non-confining. This is fixed, non-confining again. But the important thing is no movable pattern starting with plus minus 1 over k. So we can solve the degree relations and get the degrees. So this is the degree relations. This is the number of images of k, minus k, 1 over k, minus 1 over k. But ztn k and ztn minus k are completely symmetric. So we have this. So we have 4 equations, so we have this. This is an evolution equation, so we can calculate Zn, and using Zn, we can calculate degree, like this. So the degree grows polynomially, as expected. Let's move on to the last example in this talk. This equation looks the same as before, but now k is an odd integer. What happens if k is odd? This is not confining anymore. Okay, the equation is written like this, and let's fix on the same initial value problem, and let's focus on the degree with respect to z. So this is the list of singularity patterns. Of course, calculating this is interesting part of my talk, but of my theory, of my research, but I don't have much time to explain. If you use theorems and propositions, you can calculate this rigorously, even without any knowledge on this equation. So this is a solitary pattern. Gamma is not zero, not non-zero, non-infinity. And this is a non-confining movable pattern. This pattern used to be confining in the case of k, in the even k case. But this is not confining anymore. And these two fixed patterns are the same as before. So this part, only this part is different from before. And the important thing is no movable pattern starting with infinity. Yeah, this comes from the equation itself. But of course, there are a lot of propositions and theorems to show this. But anyway, so the degree relations is like this. This looks complicated, but this is practically a finite sum because of this condition. So this is the number of primitives of 0. This looks complicated because this is non-confining. This is the number of primitives of 0, and this is the number of primitives of infinity. And the delta, Kronecker delta, correspond to fixed patterns. So this equals to this. So, and taking a difference, we have this. This is an evolution equation. So we can calculate ZNT, and we get the degree like this. This is the k equal 3 case. Yes, Zn is okay, but the degree grows really fast. But this calculation is very easy because I just solved this equation. So you can calculate this, and this is rigorous. So the equation doesn't have to be confining when we use the theory. So confining or not, that's not very important. What is important is the existence of special value. Okay, let's review the talk. Okay, we introduced a new method to calculate the degree by generalizing Halber's method. We only my theory is now only work on quadratic equations, but it's expected to generalize the theory. It's the future. But we gave a framework to make the calculations rigorous. This is the important part. Our method consists of 3 steps. Step 1, calculate the constant singularity patterns of a lattice equation. Maybe all the singularity patterns. And using several singular values, write degree relations. And step 3, solve the degree relations and obtain the degrees. Okay, this is future work. What happens? What would happen if not for the d-factor condition and the basic pattern condition? These are technical things, but the basic pattern condition is more important. Some integrable equations that don't satisfy the basic pattern condition, so we have to consider some semi-basic pattern or something like that. This is what I'm doing now. And we need to extend the form of equations, like non-quadratic equation on 2D or high-dimensional case, or ordinary difference case. Because the current method is not applicable to mappings. Because the initial value problem of a mapping has only finitely many variables. That's why. That's why the current method doesn't work. So maybe this is the most difficult part in the future work. Yeah. We need some fresh idea. Okay. And in some cases, we need to extend the type of singularities because we are short of the number of linear equations. Yeah. Okay. And this is the list of reference list of this talk. So thank you.
Thank you very much, Mase-san, for being exactly on time in your talk. Now we may have questions. Now, usually when there are questions, the chairman has to ask a question, but from the very beginning of your presentations, I took a note of something I would like to ask. And the thing is, what of those things, the whole derivation you did was on individual degree.
Sorry, the whole
You did it on individual degree.
Oh, yeah,
whole
yeah,
presentation.
yes.
Now, how those things change if you do a global degree?
Yeah, so if we work on the total degree, all these values must be degree 1, right? So
exactly.
all these values must contain z. So it's not very easy to extend my theory because z star, because the key idea is this: clarify on which initial variables z star depends. So, but z depends. Z appears everywhere. Right? So this part becomes really difficult, I think. Yeah, this is just my speculation, but yeah, this must be really tough in that case.
Yeah, because you're not it turned off. No, okay. It's exactly the problem we're having when we are going to higher order ordinal difference equations.
Yes.
Because there, usually what we do, we define one variable. And study the degree with respect to that. But people are saying, no, you have to do it with respect to all the variables. And they pretend that there is the difference.
Yeah, but if you're only interested in integrability detector, then individual is sufficient. Yeah.
Anyhow, this is getting too technical, so we'll discuss it during the coffee break.
Yes.
There is a question. Yes.
Thanks. At singular points, can you try to do some blow-ups?
No.
It is possible, or
that's not necessary because I work on codimension 1 condition. So these initial values are just variables, and these are just variables. So only this part is special. So this is codimension 1 condition. So that corresponds to codimension 1 variety or something. So blow up is meaningless because if you blow up on some codimension 2 or more locus, then you have something non-trivial. But if you blow up the variety at codimension 1 locus, it's nothing. Nothing changes. So I always work on codimension 1 thing. That's why the theory worked, and that's why the pattern is completely different from yesterday's talk, like no complicated pattern appears. So blow-ups are not necessary.
Could you please give an intuition of what it means that, for example, 0 spontaneously appears?
The definition is no, this theorem, somewhere, somewhere.
On the bottom line.
ZSM is the number of spontaneous occurrences whose recurrence definition is given in definition 4.18. So it's in some other parts. So I use divisors to count everything precisely. Yeah. So divisors on P1 K bar. Yeah. And I take the degree of the divisor. That's the definition of the SM beta something. Yeah. So if you're interested in the definition, I have to recommend the preprint. Yeah. It's not very readable because section 4 is the proof part. So if you read until section 3, you know everything to calculate the degrees, but yeah, section 4 is yeah. Section 4 is based on algebras, so yeah.
Okay, so no more questions. Let's thank the speaker again.